Alright, so quickly let's talk about a quick review of what we talked about in terms of the external loads. Remember the type of loading that we have, the major type of loading that we concentrate on are geostatic stresses, the stresses associated with the weight of the material, and also we look at external stresses, or stresses associated with loading conditions that we have. For instance, if you have a structure placed at the top of the soil, that could be a bridge, that could be a fountain, that could be a building, it could be an earth dam, or the embankment that we saw in previous lectures, that induces some stresses at the top of the soil. Right? And those stresses can essentially cause failure of the soil. And failure, what is the definition of failure? It's a load or situation beyond which the system is no longer serviceable, right? So it basically loses its serviceability or its main use, in fact, as well as design part. So we have external loads, and we know that initially there are some stresses in the soil. We call those geostatic stresses or geostatic stresses. Those are the initial stresses. And then you apply the load and you have a stress increase. Remember, we call that the delta sigma concept. And we have different ways to be able to calculate that delta sigma. Remember, we talked about the Business theory, Westergaard theory, Newmark method, and ultimately the 2-to-1 method, or assuming that the distribution of the stresses happens at 60-degree angle. Alright, in terms of the stresses, remember from your geostatic stresses, the magnitude of the stresses are progressively increasing with depth, but it was in reverse when you're looking at the external loads, right? The highest magnitude of the stresses were happening at the interface or contact, and then it diminishes with depth and with radial offset, right? So those were the differences in terms of the distribution of the stresses. And then we talked about the Business theory. Business had a lot of simplifying assumptions. It basically told us that you assume that your loading conditions is perpendicularly downward. You're looking at elastic half space. You're looking at homogeneous material, isotropic material. There is no stress sensitivity concern. And all those simplifying assumptions that we have. In reality, we know that is not true. Remember in the first lecture we talked about soil are stress sensitive, non-linear, non-homogeneous, multi-phase materials, and things of that sort. So those were the simplifying assumptions, or the main assumptions that we have for Business theory. And then we talked about the Westergaard theory, which shares the same assumptions with Business theory with one distinction. What was the distinction between the Business theory and Westergaard theory? Excellent. So there is no lateral strain, meaning that horizontal strain is assumed to be zero. Meaning that basically constrain the lateral movement. So all the movement is essentially happening vertically downward underneath the loading conditions that we have. And due to that assumption, we basically talked about it induces some anomalies in the calculations, and typically the magnitude of the vertical stresses that you calculate based on Westergaard theory is much lower compared to the Business theory. Right? So if you as a design engineer, you want to figure out what the magnitude of the stresses is, a back of the envelope type thing, based on that equation, use the Business theory because it basically gives you higher stresses and therefore that influences your factor of safety. How does it influence the factor of safety calculations? How do you calculate factor of safety?
Could you be over-designing, right?
We're one step before that. We're talking about how do you calculate the factor of safety. Right, so you're basically looking at strength of the material, you calculate the stresses, and you compare the two, right? Basically the ratio of stress and the strength. You want to make sure that, for instance, for a factor of safety of 2, you want to make sure that the magnitude of the stresses are half the strength of the material, because of the issues that we might face when we are looking at construction, bad inspection, and things of that sort that you might have. And also we talked about the factor of safety is closely tied to the importance of the structure, right? So the importance of the structure, remember we talked about the earth dams. Typically the factor of safety that we use for the earth dam, because of the fact that the consequence of failure and the fatalities are going to be significant, they use a factor of safety of 9, for instance. But for the foundation of this building, depending on the mode of failure, we have factor of safety between 1.5 and 2. So that means that basically if this foundation tilts a little bit, you might see some cracks. Hopefully there's not going to be fatalities there, and then you can go in and take some sort of measures. So that's basically what we mean when we're talking about the factor of safety. We need to calculate the stresses properly to be able to properly or accurately have an estimate of the factor of safety. Right? By the way, what do you think would be the highest factor of safety? What would be the highest consequence of failure that we might have in terms of the structures? Obviously, earth dams are important, right? We talked about that awful case history that we had in 1800. More than 500 people died. But what can be higher than that?
Nuclear reactor?
Yes, nuclear facilities. Sometimes you can see that they design the structure for factor of safety of 20. So you calculate your magnitude of the stresses, and you want to make sure that your strength is right up there. Right? Even considering those, you probably heard about what happened in Japan a few years ago, right? There was a flooding issue that they had, and their nuclear reactor was compromised. All right, so that's what we have in terms of the general concept that we have to talk about when we go through. All right, we talked about the Bussiness theory. Remember, Bussiness theory considers a point load, right? Now, if you want to determine the distribution of the stresses for other types of geometries, what should you do? You have to integrate that, right? So if you're looking at the line load, you basically integrate that point load along the line. How about if you're looking at a rectangular shape? A typical foundations that you see, which is similar to what you see in this slide here. Now, what should I do in this specific case? I have the solutions for point load. Now I want to figure out what would be the distribution of the stresses and the magnitude of the stresses with depth and the radial offset that you might have. So for this specific case, now you have to do a double integration, right? And that double integration essentially tells you that you have that equation there, and you do the double integration both along the length and the width of that rectangular shape footing, right? So this is the process. So here's what you have to do. You have to do a double integration there, and we had the Q here, and you had, remember we talked about that I value or the influence factor? Influence factor essentially acts as a reduction factor for you, meaning that you have in this equation, you have delta sigma equals to Q, which is the distributed load on the surface, multiplied by an I value or influence number. And that influence number becomes smaller and smaller as you go down the depth and as you move away from the point of application of the load that we have. Now the challenge here would be calculating this I2 value that we have here, which as you can see, it's a function of B over Z. That would be B. Z would be the depth that we are interested to calculate the stresses at, and L over Z, which would be the length of the footing that we have over Z. So you have the normalized value of M and N, and you end up with this monstrosity here. Right? So in order to do the calculations here, what you can do is you can use graphical methods. Right? Nowadays, doing these calculations are relatively simple and straightforward. You already have the spreadsheet that I already posted on the website. You can take a look at that. All these equations are already embedded in it. Right? Instead of doing that, you can also use graphical forms. So let's quickly talk about that. But let's just see what these equations are essentially concerned. We are looking at M value and N value. Those are the ratio of width over Z and depth over and length over Z that we have. So if you do that calculations based on the geometry of your footing, and you know what would be the depth that you're interested to do the calculations at, then you end up going and using this graphical graph. So let's see what we have here. Notice that I'm interested to calculate the change in the magnitude of vertical stresses. That would be the delta sigma Z. That's the objective here, right? And for that, I can just multiply Q naught, which is Q naught is the distributed pressure on the surface that we have, multiplied by an I value. You use this graph to be able to estimate that I value. Previous slide, we saw that it is a function of those M, N, and Z value with all those big huge equations that we have. So instead of going and doing those calculations, what you can do is you can basically use this graph. Let's quickly take a look at what this graph gives us. On the x-axis, you have the N value, N as Nancy. It's Y over Z. Has to do with the dimension of the footing that we have, and the depth at which we are interested to do the calculations of the stresses. What else do we have? You have M value, which is X over Z, and that would be this value divided by the depth that you're interested in calculating the stresses at. So let's take a look at how we can use this equation. You simply calculate your M value and N value. You select the N value on the horizontal axis. The value of M is the values on the curves. So you just go up there, you select this, let's assume it's half. And you move up and you hit the curve that represents the M value, and you offset that either on the left-hand side or the right-hand side, and that gives you the I value, right? So we use this plot to be able to estimate the I value. Okay, let's go one step back. What's the general objective here? I want to calculate the sigma z, right? The vertical stresses. The vertical stress is equals to pressure on the surface multiplied by a reduction factor, right? The I value, we call that the influence number. And influence number, you can estimate that based on this plot here. For that, you need to know the geometry of the footing that you have, right? M value and N value, those are the B over C, L over Z value. And then you mark that on the x-axis, mark the value on the curve, and you offset that on one of those vertical axes that you have on the two sides, and you can get the I value. Once you get the I value, you can simply multiply that by the pressure at the surface, and you can get your sigma z, right? It's very simple and straightforward in that specific case there. All right. One thing that you have to, or two things that you have to note about this plot is that first, M and N values are interchangeable, as you can see on the plot. Implication of that is, don't worry about which one is length, which one is width, right? Just stay consistent along the problem solving and solutions, right? So that's one thing to note. The important part is this equation, or this plot, gives you the stresses at the corner of that footing. Not at the center of it, not at any point within the footing, not any point outside of that footing. It gives you on the corner. So how can I use this plot to be able to get the values for other locations? For that, we need to turn everything off and hope that we can come back again after turning this off. All right. For that, we use a method that is called the method of segments. To simplify that, let's subdivide things into four cases. Let's use case one. Sus, no? Is it visible from back there?
No, it's not.
All right. So case number one. This would be for the case that you want to calculate the stresses at a corner of this rectangular shaped footing. That's A, B, C, D. And let's assume that I'm interested to calculate the stresses at point A. How do I do that? I just saw that you can calculate delta sigma as a function of Q naught times I. And that I is associated with I, A, B, C, and D, right? In this specific case, you have N value, which is L, let's call this one B here. What was the M and what was the B? You can do whatever and that would be fine. It's interchangeable, right? These are called normalized dimensions. What's the benefit of using the normalized values? It means that it's independent of the units that you use. You can use English units, you can use SI units, and basically everything cancels out, right? So these are normalized value, and you can, the general form of the equations, or the general form of the plot is coming from the general forms that we have. Remember you had n value here, and then we have curves, and then you have I values, right? And these were n. So essentially what you have to do is move up there and read the I values. Simple and straightforward, right? Alright, so that was case number 1, which was the easiest case, right? How about if I want to calculate the stresses at midpoint? Let's call this one K. Can I use this plot? This plot gives me the information on the corner. Right? What should I do? Divide them, right? Excellent. So this is what you have to do, basically. What is your M and N value in this case? Right. So in this case, you have, let's call that N prime. That would be M over 2 divided by Z again. And you have B over 2 divided by Z again. Now, tell me what my equation would look like in this case.
Is that a Z or a 2 on the M prime?
It's a Z. It's the depth. Alright, so here, I'm assuming that the superposition of loads are valid, right? So I have 1, 2, 3, and 4 here. So this means that I basically subdivide this into 4 rectangles here. And in this specific case, all these are equal to one another. So what do I have? Do you agree with that? It's 4 times one of those. So you calculate it for 1, multiply it by 4, and you can simply do the calculations. So now let's make things a little bit interesting. So let's assume that I want the point K, but point K is no longer at the center. It's just one arbitrary point within the loaded area. A, B, C, D, A, C, D, F, here, G, H. Now in this case, your delta sigma is this equation. They are no longer equal to one another, right? So you have, again, 1, 2, 3, and 4 segments. hence the word method of segments. And you can calculate the B and H for each specific case. Notice that this one would be L1, L2, so you have to have L1 over Z, B1 over Z for each specific case. So you have to be careful about the selection of the B and L values for method of segments that we have. Questions? Clear? I'm going to erase this. We want to go forward. All right. And can you think of any other type of stress calculations that you might be interested in? Now, what if I want to calculate the stresses at a point that is outside of this loaded area? In real life, it would be, I'm interested to calculate the stresses 5 feet away from the foundation. Ricardo is interested to calculate the stresses at a few feet away from the foundation of a pedestrian bridge that he is working on for his senior design. This would be the case. How you can do the calculations here. All right. So what should I do? The desired point is outside of the loaded area. I know that this equation, or this plot, gives me the stresses at the corner. What about this one? The general form of the equation is delta sigma equals to distributed pressure, that you get it from your friends in the structural engineering, right? That gives you the magnitude of the stresses on that column, for instance, times an influence factor. So,
Subtract. That's it.
the main point, the most important point here is that we are looking at rectangles here. All these rectangles have to share the desired point. The desired point is K. K should repeat itself in all the segments that you have. So what you can assume is, you can assume that the whole area is loaded and then start subtracting segments. What's the whole area of loaded then? K, H, C, E. Do you agree with that? Let's assume that the whole thing is loaded instead of A, B, C, D, and then start subtracting the segments. All right, so tell me what I have to subtract. Rule number 1 of method of segments. It's more like you have to make sure that the K point is always in that
K,
yeah.
yeah.
So you have, let's assume that KGED, I subtract this. The second part, I subtract this.
You have to add the other one back in.
And then since I subtract this part 2 times, I'm going to add this one. It also shares the K point. KGDE minus influence factor of, again, KHBF plus influence factor for KGA. assuming that the whole area is loaded, and then you subtract two long rectangles there and add those roughly square shape on there. All right, so you have to consider two things when you're looking at the method of segments. One, the desired point repeats itself in every single influence value that you do the calculations for, right? The second one is you have to make sure that you're properly selecting the B and L values for each. The B and L value for these segments are different from one another. This would be the B value and this would be the L value, for instance, for K, H, C, E, right? Now, how about for this one? This would be these two. So they're different. The only thing that is different in each of these influence factors are the length and the width. The Z value or the depth that you're interested to do the calculations at is constant, right? Because, for instance, you want to calculate the stresses at 2 meters below the surface, 5 meters outside of the rectangular shape footing that we have, right? So this is what we can do instead of using those spreadsheets that we have posted on the website. For your homework assignment, you're going to use this method of segments to be able to do the calculations. All right, so now let's move forward with an example here. All right, we are looking at a rectangular shaped loaded area. That would be the footing or the foundation of a building. That would be F, H, G, B, or the one that is shown with blue here. I'm interested to calculate the stresses at point Y and at the depth of 5 meters below the surface. Which case is this?
4.
It's case number 4, right? You're looking at the point outside. So for that, you have to do method of segments, right? For the method of segments, what should I do?
Find the area of the whole thing.
You just basically have to look at where the point is and start adding and subtracting the segments to be able to get to the area of loaded. This is the loaded area, and the superposition of loads are valid. So you can add and remove and end up with the same external stimuli that we have, which is basically, in this case, would be the strain of the material. All right, so tell me what kind of segment you choose here. You know what the general form of the equation is? Delta sigma equals to Q. The distributed pressure, it's given here. And then you need to know the I value. The challenge here is finding the I value, or the influence factor. We know for the rectangular shaped footings, you can use the plot, right? For the plot, what do you need to know? You need to know the M value and you need to know the N value, right? For M and N value, what do you need? Length and width
Yeah,
for each specific case. The depth is also given here, right? So we know what that depth is. So for that, you need to do those calculations. But one step before that is doing the segmentation properly. All right, tell me what we typically have to do for the case of outside point. Outside point is Y. Remember, the first step is to assume that the whole area is loaded, and then start removing the segments to end up with the loaded area, right? All right, so tell me what your I value is, the first one.
YACB.
So the first one that you look at is YABC. That would be the total area of load. What would be the B value for that? Let's assume that this is B, for instance. 15, and you have 10 here, right? And what is the depth that we are interested in? 5, right? So tell me what the M and N value here is.
3 and 2.
Right, so it's 3 and 2. Does that make sense? Right. It's very simple and straightforward. All right, so removing the segments. YAFD, that's 1. It also shares point Y. YEGC, Again, it shares point y, so we're good. And since we subtracted this segment twice, we're going to add YEHD at the end of the day. Right? Easy, simple, straightforward, right? Now what you can do is, you can basically develop your own Excel spreadsheet for that, right? So the first one would be, as you mentioned, is YABC minus YAFD. What is YAFD? This one. YEGC, and you add this segment at the end. Right? So you have the X and Y for each of those, and you have X over Z, Y over Z to be able to get those M and N values here. You get your M and N value. Once you get that, you have to go to the plot, right? You go to the plot and you make the selection. Let's quickly take a look at one of those together. Assuming that your N value ended up to be 2, as you mentioned, and you're calculating the stresses for, this would be 3, right? And then you go and offset that number on the horizontal axis. It's going to be close to 0.23 or something like that, or 24, right? And remember that these are reduction factors, meaning that you multiply that by the stress on the surface, and basically it's going to be smaller than that. In this case, basically that number is going to be roughly 1/4 of the contact pressure, 124, 125 here. That's the implication of that. Alright, so once you do that calculation, you basically end up with different I values, and you simply multiply that 100 kPa that we had at the contact pressure by this, and you calculate the stresses, and it turns out to be 0.3 kPa. So where did we want it to calculate the stresses at? We wanted to calculate the stresses at 5 meters outside and 5 meters down below the depth. What did I end up with? 0.0 kPa, extremely small amount of stress, right? That makes sense, right? Where do you think would be the highest magnitude of the stress?
Dead center of the load.
Center of the load is correct, and right beneath, right? So right at the contact. So that would be the maximum stresses. If you do the calculations, in fact, you will see that that is going to be roughly 1/4 of the contact pressure. So I'll leave that up to you, so take a look at that. So if in your exam I ask you that explain your result, you can also mention that the small magnitude of the stresses is an indication of the dissipation of the stresses with length and with depth, right? So that's how you can explain that. Now let's quickly talk a little bit about, maybe in 1 minute, about one of the implications of what we have here. Many of you seen that in new designs, in luxury homes, they put a big, huge swimming pool at right at the slope, right? Because they want to have the view, right? So right at the slope, you have the swimming pool. What's the implication of that? You have swimming pool, concentration of mass right at the slope, right? And a lot of times that you see when they didn't reinforce the slope fails. This is the reason for that, right? Because the magnitude of the stresses are high right at the edge, and it will result in the failure. So that's one example that you might consider when you're looking at the usage of these applications. All right, so now we can quickly move forward and take a look at other types of foundations that we have. We have circular foundations. Previously we looked at the rectangular shaped foundations. These are circular foundations. Typically we use them for bridges and silos in general. The general form of the equation looks like this. If you want to do the calculations at the middle, along the center line of the loaded area, and as you can see, it's a function of the radius of that foundation as well as the depth that you're interested to do the calculations. So very simple and straightforward. You can use that equation, or you can use that plot in there, and it gives you the information about the distribution of the loads. Now let's take it a little bit further. If you want to calculate the stresses at x away from the center line and also at the depth z, you use this equation. Notice that the form of the equation is very similar to what we talked about before. It's I multiplied by surface pressure. Now, where do you get the I? For that, we have a different type of plot here. This is the plot specifically for circular loaded areas, right? Previously we looked at rectangular shaped areas. But this is very simple and straightforward. You really don't need to go through the method of segments, and based on this plot you can simply calculate or determine or influence number. So tell me quickly, what values are we looking at in different axes? On the horizontal axis here, we are looking at the I values. This is what is required or the objective. On the vertical axis, we are looking at the normalized value of Z over R. Z is the point in question. R is the radius of the loaded area, right? And what else do we have? This is the radius that we have. The geometry basically is self-explanatory. And then we have numbers on the curves. Numbers are the curves on the curves are x over z, x over r's in this case. X over r, which is basically the offset away from the center line of the loaded area. And for x over z of 0, what would be x over z? X over z of 0? That would be the case of x equals to 0. That would be right along the center line, which is the case that we looked at in previous slide. Make sense? Alright, so that would be this curve, and then the values are going to be larger and larger as we move away from the point of. So you can use this plot to be able to calculate the I value. The process is the same. You just have to determine the I value and multiply that by the surface pressure there. Now, what if we are looking at an embankment? Now, this would be the case that you might have a vehicle that is passing over an embankment and you want to figure out what are the stresses that are associated with the vehicle, for instance, right? So in this case, we have a different type of plot. Again, the process is the same. You have A and you have B, and this plot that we have is essentially functions of A, B, and obviously the Z that you're interested to do the calculations at. The general form of the equation is again the same, I multiplied by Q naught, and I is the one that we want to figure out based on this plot. On the horizontal axis, you have A over Z's. It's a simple calculation there. And also you have values on the curves are B over Z's. A and B's are essentially from the tapered off load, that would be from here. It has to do with the geometry. And B is going to be from the point of tapering off to the center line of this embankment that we have. So that's basically another way to look at the stress calculations based on graphical methods using the Business field. And ultimately, if you're interested to do the calculations for the case of a rectangular shaped distributed load, beneath the corner O and beneath the corner Q, you can use the same set of equations, same set of M and N values, and in this case you can use the two plots that we're looking at in this slide there. So these are essentially the ways that you can do the calculations of the stresses associated with the external loading conditions that we have. Alright, so that was for the Business theory. Again, one way to do that is use your calculator and spreadsheet and punching all those equations in there to be able to do the calculations. The second one was looking at graphical methods, right? Now, we are looking at another graphical method, and that has to do with our Newmark method, which is a variation of the Business theory that we have. Alright, so the main advantage, or first, the main reason that we have to go through this is because I've seen several times it shows up in the FE tests. Nowadays, probably not a lot of people are using this method, but it would be a good idea to learn that because you'll be tested on that in your FE test. But first of all, let's see what this Newmark method is about. Newmark method is based on Business theory, another graphical method, but the main advantage here is that you can have irregular geometries for the foundation. So let's assume that you have half-circle foundation, right? Long view, it looks like a half circle, or it looks like an L-shaped, right? So you can use that geometry to be able to quickly calculate the magnitude of the stresses at any point within the soil and at any radial offset in that soil. There is one general equation here. The general form of the equation is very similar to what we saw before. The stress increase in vertical direction, delta sigma z, equals to Q, which is the contact pressure that we have. Again, similar concept that we had before. I, in this case, I is the legend that you have up there, the I value. In each plot, you have an I value here. 0.001. So it's very simple, just have to read that off the chart. Now, the challenge here is this n sub s. N sub s is the number of segments covered by the rescaled foundation. Now we have to talk about that. Right? Again, the general form of the equation is this. The first and second terms are simple and straightforward. The third term is what we have to figure out based on this plot here. You with me? Alright, so let's move forward and talk about how we can get this n sub s value, or the number of segments covered by the rescaled shape. Alright, so first of all, what we have in this plot is we have an I value and we have a scale. That OQ, as you can see here, right? So the first step is rescale your geometry. We'll talk about that. So let's assume that I'm looking at a rectangular shape footing, right, in this case. First step is I have to set the scale to the depth that I want to calculate the stresses at. Let's assume that I want to calculate the stresses at 5 feet down the depth. So I set this one as 5, right, and rescale my foundation. Right. So I rescale this one based on the depth scale. I outlined that in the next slide, so don't worry about that. It's stepwise, so you can take a look at that. But right now, let's figure out if we can move forward with the general concept here. All right, the first step is set the depth scale equal to the depth, and then replot your foundation. Let's assume that now this foundation is based on the new plot, and then place the foundation at the point that we are interested to do the calculations at the center. So for instance, if I want to calculate the stresses at corner, I put this one in the corner. If I want to calculate the stresses at center, I move that to the center. If I want to calculate it at 5 meters away, I push that 5 meters away. Right? And then I calculate the number of segments covered by the rescaled foundation. And that is the n value that we have. Obviously, as I move away from it, the number of segments are going to be less, and therefore the magnitude of the stresses are going to be smaller. Right? As you move right in the middle here, the number of segments are going to be more, and therefore the magnitude of the stresses are going to be higher. So in very simple terms, each segment represents a certain magnitude of the stresses. The higher would be that number, the higher would be the magnitude of the stresses imparted on the material. It's very interesting how they develop these plots, right? Nowadays, we just use our calculator to be able to do the calculations. So this was for the very simple case of a rectangular shape. Now imagine if it was a very weird geometry there. That would be very useful, right? You didn't need to do the small segmenting and figuring out what the magnitude of the stresses are. So let's quickly go over the general process as we talked about here and solve a numerical example. All right, here's the process. Set the depth scale shown on the chart equal to the depth at which the increase in the vertical stresses are required. The second step is identify the point on the loaded area below which the stresses change is required. Remember that point A. Could be at the corner, could be in the middle, or could be somewhere outside. Plot the plan view of the loaded area using the depth scale, and ultimately count the number of segments covered by that rescaled geometry. So that's basically what we want to do. In that general form of the equation, the only thing that you don't know is the n sub s, or the number of segments, and the rest of it is very simple and straightforward. You have a q, which is typically given, you have I, you read it from the chart, and you determine that value there. So let's quickly solve a numerical example. Hopefully that will help things fall in place a little bit better. Use of Newmark's chart to calculate the stress increment at point A at a depth of 3 meters. Alright, so let's figure out where the geometry is and where we're looking at. So this is our footing. It's 3 meter by 6 meter. And I want to calculate the stresses at 1.5 meter away from the center line. Right? And we are looking at plan view. And at what depth we want? We want it at depth 3. 3 meters below the surface. Right. So this is the general geometry that we have here. All right, so tell me in the general form of the equation, what do I have and what I don't have? Do I have the Q? Q was surface pressure. Surface pressure is given. I need to know I. Do I have I here? Remember, for the Newmark's method, I is the value that shows itself on the chart. What is it? 0.005. So I do have the I value here as well. If you're wondering where this comes from, it's basically 1 over the number of segments in the chart. That's where it's 1 over n, basically. So we have the I value, we have the Q value. What do we want?
And
We need to figure out what those segments are. All right, so what is the depth? The depth is 3 meters, right? So I have to set the scale to 3 meters. Agree? Depth scale. All right, so this is my scale. I set this one as 3 and rescale my foundation. Right? So if it is 3, this would be unit, same as this one. This is 6, therefore it would be twice of this value. And this is 1.5, therefore it's going to be half of that. Right? Very simple and straightforward. Right?
So the width is always the scale, right? Not left, not.
All of them.
Oh.
All of them, yes. Any segment is going to be basically based on the depth scale. So this is going to be exact. All right, so you rescale this one, and we want to calculate the stresses at point A. Therefore, you have to slide this one to the center. Right? You want to calculate the stresses, and this would be the point that is interested. You have to slide it over the center, and you have to start counting the number of segments. Right? Notice that some of these segments are not whole. You just calculate them, and you get an estimate, you sum them up, and then you use an integer number. Right? So it's very arbitrary if you want. So if you look at that, that would be 30 segments that is covered by the rescaled shape that we have, and the magnitude of the stress is up to be 45 kPa. Yes? At 0 meters, right? That would be the magnitude of the contact pressure. At 1 meter, so your depth scale in that case is going to be 1. Therefore, your shape is going to be larger or smaller? Could be larger, right? And therefore, it covers more segments. Therefore, the higher would be the value of the stresses. Yes. And notice that this is an estimate. In fact, the next method that we talk about, we do a numerical example, and you see the side-by-side comparison of all these methods that we talked about. All right, so this is what you have, and I would suggest you take a look at that before you sit for your FE test. All right, so let's quickly talk about the other method, and that would be the last method that we have for the stress calculations. It's also called the 2-to-1 method, or assuming that the distribution of the stresses happens at 60-degree angle. Right? So that's basically what it means. We are looking at 2-to-1. That would be 2 vertical, 1 horizontal. That would be the triangle that is created by 2-to-1. And if you look at the slope of the distributions are essentially 60 degrees. In very simple terms, you're using the trapezoidal group. We're assuming that this is the loaded area. This would be my Q, right? Distributed pressure. And then you have the area here. B times L, right? B times L times Q, what does that give me? The load, right? You're looking at the stress, you're looking at the area, and you're looking at the multiplication of the two together, that gives you the load. And essentially tells you that that load distributes at a 60-degree angle, and you can use the trapezoidal rule to be able to get the value of the plane that these stresses are essentially distributing against. You have an approximate stress distribution, assumes that the total applied load on the surface of the soil is distributed over an area of the same shape as the loaded area on the surface, but with dimensions that increase by the amount equal to the depth below the surface. And that's the definition of what we have in these equations. So essentially this tells you that Q naught times BL, that gives you the load, right? Pressure times the area. This is my area, B times L, times Q naught, which is the distributed pressure on the surface, that gives me the load. And denominator is essentially the area, right? B plus Z, L plus Z, and that would be B plus Z and L plus Z that I have here. So it means that now the load is essentially distributed over a larger area. In very simple terms, it means that the magnitude of the stress is now went down, right? Same load magnitude, but it distributes along the larger surface. The denominator increases because Z increases with depth, right? And ultimately it results in the lower magnitude of the stresses. Alright, so this is basically the two equations that we have. Now let's pull everything together with one example and see the magnitude of the stresses associated with each of these methods that we talked about. Alright, we are looking at a footing, 3 meter by 3 meter, and we want to calculate the stresses in the middle, and we have the bearing pressure on the surface of 145. We want to use the Glisson-S method, we want to use the 2-to-1 method, and we want to compare our results and see how these calculations are compared with one another. Alright, based on this segmentation that we have here, which case are we looking at? We want to look at the stresses in the middle of that foundation. Case 1, 2, 3, 4.
2, 3.
Case 1 was on the corner of case 2. Case 2 was in the middle, right? So tell me what the B and L values are for this specific case. So 3 meter and 3 meter, right? Would be? Go back to your notes. We had case number 2, delta sigma equals to 4 times Q times I, right? And that I was associated with that smaller segment that we have, right? B over 2 divided by Z, M over 2 divided by Z. 1.5 divided by 3, again 1.5 divided by 3. Everything multiplied by 4 because superposition of modes, right? Is it clear what we're doing here? All right. That would be for the case of Glisson-S theory. For the 2-to-1 method, we have one equation. So let's quickly take a look at that. That was the M and N values that we just talked about. The B value and L values are 1.5. The depth is 2 meters. We looked at 2 meters, right? Yes, that was 2 meters. And then that would be 0.75. So you select those. That would be where you look at essentially. That would be right here, 0.75 that we have. Choose 0.75. If you don't have the points, you just interpolate between the curves. Right. And then read the value on the y-axis or the vertical axis. That y value ends up to be 0.13 here. And as you mentioned, this is case number 2 that we talked about. This would be delta sigma equals to the distributed pressure times the influence factor associated with each of those segments. Because of the fact that these segments are essentially similar and equal to one another, that would be 4 times Q naught times one of those i's. And notice the values. If you do the calculations, 4 times 145 times 0.13 ends up to be 97. Now the second case would be when you use the trapezoidal rule, or that 60-degree distribution that we talked about. You have the B and L value, you have the distributed pressure, you have the Z value, just one equation, and you end up with 52. Previously, it was 70-something, now you have 50-something here, right? So which one is more conservative, which one is less conservative? The one that is higher is more conservative, right? Which was the Glisson-S method, right? So Glisson-S method results in more conservative values compared to Westergaard and 60-degree distribution of the stresses. Right.